How do you make an underpowered, slow 8-bit CPU seem a bit more capable than it really is? Interrupts. That mechanism where the CPU can be poked at and told to do something completely different, then it can resume whatever it was originally doing as if it had never stopped. On the Spectrum, and in this instance I mean the original 16 and later 48K Spectrum, this was done in a typical Sinclair way, cheaply, with as few components as possible, leaving the majority of the work to the programmer. Let's look at how these devious hardware designers crafted a cheap and functional system that didn't exactly follow the Z80 specs. Now, if you've watched other videos, you might be thinking, what's so special about interrupts? I mean, I've already explained the concept and they're not that difficult to understand. Well, we're going to look quite deeply at how they actually work on a Spectrum, because it's pretty special. You see, the Spectrum was made to be cheap, like super cheap, cheaper than any other home micro. And unlike cheap computers at the time, it was designed to actually be a usable computer. Now, cheap computers of the time had this nasty habit of being severely crippled in one way or another. Maybe they barely had any RAM, so you couldn't actually load anything interesting into them. Or the graphics were so low quality that you couldn't generate anything that was interesting. To make the Spectrum cheap, they put as little hardware as possible inside it. Like inside a 48K Spectrum, there's barely anything. Compared to a C64, which had a SID chip and a VIC2 chip and I/O controllers and lots of RAM that always breaks, there's none of that in the Spectrum, just a big ULA, a CPU, some ROM and some RAM chips. From a computer science and design point of view, this is quite interesting. By poking around in these bits of old machines, you can learn things, and it's quite what I like to do. One of my most popular videos is me poking a Z80 using an Arduino, just to figure out exactly what the chip is actually doing. Interrupts are in that sort of same category of exploration. Anyway, back to the video. Interrupts on the Spectrum. Let's see if I can get through this without interrupting myself with too many tangents. I've got a whole spectrum of bad puns though. So, CPUs are machines, and they follow very precise and mechanical processes. They fetch, they decode, they execute instructions one at a time. Some instructions take multiple cycles to complete, but it's all very precise, very exactly timed. Every time the CPU's clock ticks, the CPU does a very specific task. Now, the real world isn't quite as predictable, because a laptop running on battery doesn't know precisely when its battery will go critically low until that actually happens. Your computer has no idea when you're about to press a key until you press one. Now, one way to deal with this is called polling. This is where the machine sits in a loop and it constantly checks for something interesting happening. It consumes a lot of CPU time, means you could miss important time-sensitive events. It's like a kid in a car, constantly asking, "Are we nearly there yet?" every 30 seconds, until you kick them out of the side of the road. Interrupts let us write more sensible code. Instead of polling, we can configure our devices to trigger interrupts to tell the CPU something needs its attention. Now, the CPU will then do internal housekeeping, drop whatever it's doing, and move on to dealing with the interrupt. So, for example, when a printer runs out of paper, it can send an interrupt to the CPU. The CPU can act on it. Now, saying printer out of paper is a bit specific really, but you might have a printer wants attention interrupt. That seems more logical. Or your disk drive wants attention. Or even the screen has been drawn, the electron beam is about to go to the top again. Now that last one, that's important. That's called a vertical blank interrupt. It's kind of key to the Spectrum's workings. It's quite fundamental to its operation. So if you go looking online, you'll find websites like this one, which they calmly and they clearly explain the wonderful system of an interrupt line on the CPU and the concept of daisy-chained interrupts, each device cooperating with the others to spread this wonderful organised system of politeness throughout the system. Feels exactly like the thing a British-made machine would do, right? The devices politely wait their turn in a queue. Maybe the most important device, probably the ULA, can assert an interrupt, and then lesser devices like the expansion connector or video circuitry can also do that, but politely wait their turn until the ULA is no longer busy keeping the machine alive. But no, not really. This is what reality is more like. You see, Sinclair were in an arms race to build the cheapest computer possible to beat their competitors. That meant using as little hardware as possible, making the hardware work as cheaply as it could. Should do a video on the Spectrum's video hardware. There's some cost-saving cleverness in the way that works too. It explains all the funky colours and stuff. And that's where the story of them using faulty RAM comes from. They bought RAM where half of it was broken and wired up the working half. and just use twice as many chips. It's called binning, and it's still done today. Partly broken RAM is cheaper than fully working RAM. Making a tiny computer from thin plastic and rubber keys, cheaper than building a beige bread bin. Especially if you're a calculator company and you already know how to make that kind of technology. Oh, damn, I've interrupted myself again. Now, there's two types of interrupts on the Z80, by the way. There's the ones we're looking at, which are properly called maskable interrupts because they can be ignored. And then there's non-maskable interrupts, which the CPU is unable to ignore. We're not going to deal with those. We're just looking at regular interrupts, and the Z80 has 3 interrupt modes. It's got IM0, IM1, and IM2. So let's look at each one. IM0 is weird. A peripheral can assert an interrupt and then put an instruction directly on the data bus. The Spectrum doesn't use this at all. IM1 makes the CPU jump straight to address 38 hex. This is hardwired into the CPU. It then executes whatever code it finds there. This is what the ROM uses. Now, IM2 is more interesting. Let's take a look. In IM2 mode, when an interrupt occurs, the Z80 jumps to what is known as an interrupt vector. It's a table in RAM containing 256 bytes. Each entry in this table is a pointer to an address in RAM containing an interrupt handler. So when a device raises an interrupt, it's supposed to put a value on the data bus that is interpreted by the CPU as being an index into that table. It's quite a clever system, especially for slow CPUs. Except not in the Spectrum. No, let's cost reduce this idea to its smallest, barely functional minimum. How about we just have the vertical blank interrupts, because we have to have one of those to get the screen working. The ULA can fire this off every frame once it's finished drawing the screen. And because this is the only interrupt on the entire system, let's not specifically set anything on the data bus, because there's no point, it's the only interrupt there. Except the Z80 in the Spectrum isn't any different to any other Z80. It still works the same. It still assumes that you're going to put some data on the bus to tell it where to go. So what happens when the CPU gets a V-blank interrupt? Well, it'll do its internal housekeeping tasks, then skip off to its interrupt vector table. It'll then look on the bus for data that will tell it the index into the table. Except nothing's set one. The data on the bus is now random. So it's just randomly executing arbitrary code every time it gets a V-blank interrupt. So how do we deal with this? Because this is all how the hardware works. We can't change it. Well, what we do is we get crafty. You see, the value on the bus can be anything, but it can only be in a certain range from 0 to FF. So what we need to do is somehow construct an interrupt vector that contains 256 pointers that all go to the same place. That way, no matter which entry the Z80 happens to pick, it'll go where we want it to. However, there's a few things. Because these are 16-bit addresses, if the CPU looks in the interrupt vector table, it's going to read 2 bytes. And this means that, firstly, our vector table needs to contain 257 entries. Because if it happens to pick location FF in the table, it's still going to read 2 bytes. So we need an extra byte to go over the end of the table. Secondly, all 257 entries need to be identical. Because if it got 00 on the bus, it's going to take byte 00 and 01. If it happened to randomly get location 01, it's going to take bytes 01 and 02. So what you can do is create a table at location 8000 hex with 257 bytes, all containing the value 81 hex. This would then tell the CPU, no matter where it went in the table, to go to memory location 8181. And at that location, we could then put our code. Now this has the annoying side effect of wasting 257 bytes of RAM. On a machine with 128K or more, that's not really a big deal. On the original 48K Spectrum, it's possibly more important. Now there was a sneaky technique though, which I'll use the excellent Break Into Program website to explain. Not going to read it out, it's on the screen at the moment. I'm sure you've managed to read it before I finish waffling on this little bit of filler. So, cheers Sinclair. If you're a hardware person, you're probably looking at that and thinking it's an excellent example of 1980s simplicity for a cheap home computer that was originally a bit of a kid's toy. If you're a programmer who's never really got down with the hardware, You're now looking at this, probably wondering why hardware people hate us so much. That's why this video is here, to help kind of explain and demystify why this system exists like it is. It's not just that they're being mean to us. And I could just say, here's some code, put your routine in here and off you go. But it's more interesting to understand why this is the way it is. If you want to see code, my GitHub is linked below with an example. It's written in C using Z88DK. And you might find that useful, as there's some compiler constructs that you need, and they're not really documented too well. Now, by understanding why these things work, we can not only properly understand the machine, which helps with debugging, but it also lets us have some insight into the original creators of these machines and what they were thinking. The interrupt system shows that very clever kind of hardware hacking that people do when they've got lots of constraints. It's barely functional, but it's good enough, just like the original Spectrum. There we go, that's the weird world of interrupts. It's not that useful, unless you know you need them, but it's educational, poking around at this sort of stuff. So come back next time for a more practical technique where we play with a new feature on the next, its DMA controller. If you're still watching, well done for making it to the end. Do me a favour and press the subscribe button if you haven't already. Maybe share the video if you think it deserves it. And until next time, I'll see you later.